that, let me introduce Professor Chuan Haitao from Peking University, and he's going to talk to us about path integral approach to heat and work. So please take it away.
Okay, so can you hear me?
Yeah, absolutely.
Okay, good. Okay, good afternoon, everyone. My name is Haitao. First of all, I would like to thank the organizers, especially Jusa, Peter, Tapu, and Yajindra for offering me this opportunity. This is a very wonderful workshop and benefit a lot. And also today I will give a talk about the quantum Brownian motion and heat and work. This is a joint work with my former postdoc, Funo Ken, and he's currently in Riken in Japan. And this is our, oh, sorry. Okay, well, oh, so there seems to be some weird things happened because when I tried to invert this, can you hear me?
Yeah, Professor Chuan, I think you just have you tried clicking on the slide? Sometimes if you click off the slide, then so just click.
Okay.
Yeah.
Okay. So I don't know what happened. So
yeah, there you go.
But this is I tried to. Okay, so let me do the full screen mode. Is that okay?
Yeah.
Okay, good. So this is the outline of my talk, and first I will give the introduction to the background and the motivation, and after that I will introduce the main concept that we introduced. We call it trajectory heat along every pair of Feynman paths, and in the third section we will formulate Jaginski's equality and the so-called microscopic reversibility based on the trajectory heat that we introduced. And in the fourth section, we will demonstrate the quantum to classical correspondence of trajectory heat, as well as the heat statistics. And finally, we give the summary. Okay, so let us start from the classical open system. And as you may be familiar with, that in the field of stochastic thermodynamics, people usually use the Brownian motion as the typical model. And by introducing the so-called work and heat functional along an individual trajectory, people are be able to formulate the so-called fluctuation theorem. And here, the key concept is the so-called trajectory work. And it's identified as the energy change of a system. For example, the Brownian particle, the energy change when the external parameter lambda is changed, but keeping the microscopic state of the system, that is coordinate of the system, fixed.
Excuse me, Haitao, sorry.
Sorry?
Just still, we all can see, I think, only just your outline slide at the moment.
Sorry, can you say again?
It's just the outline slide that we can see at the moment.
Oh, you can't see the slide?
No, we can see the slide, but it's just the outline slide. The one on which you have put your outline, I think.
Okay, so you don't see the slide that I'm showing?
No, exactly.
Oh, okay, so right. I'm sorry for that. Okay, did you see which slide I'm seeing now? The trajectory
So this is the trajectory work and heat in classical stochastic systems.
Yes, that is what I'm showing.
Right. We just saw it right now. It just changed right now for us.
You changed? Oh, okay, so let me, yes. Okay, sorry for that. No I tried to, okay, can you, let me try again.
Okay, so I don't think your slides are actually going into a full screen mode.
I'm trying to go to a full screen mode, and let me see what happened. I mean, so maybe what I want to do is the following. I will first change it to a full screen mode, and then I will share my screen.
No worries.
Let me see.
Yes, sure.
Let me see if it will work. Okay, sorry for the inconvenience. Okay. Let me see. And seems that let me share. Desktop and screen. So can you see the
now it's in the full screen mode.
Yeah.
I think this should work now.
Can you see
Yes.
Okay,
the
good.
next slide, the first law.
Yeah,
Right.
yeah,
Perfect.
very
Thank you.
good.
Okay, good.
Yeah, thank you.
Thank you. Sorry for the inconvenience. Okay, so I think the key concept is the introduction of work and heat along an individual trajectory. And that was proposed independently by Chris Jasinski and Ken Sekimoto in around the year 1997. And the equation of motion for this Brownian motion is usually the overdamped Langevin equation. So by substituting the equation of motion into the original definition of work and heat, one can further write down the expression for trajectory heat and trajectory work. And one can also formulate the first law along an individual trajectory. For example, this is the equation of motion, and this is by dividing this internal energy into work and heat, one can formulate the first law along an individual trajectory. I would call this is a refinement of the first law, because when you do the ensemble average, you will obtain the usual first law. And besides the first law, one can also consider the extension or formulations of the second law. And thanks to the work of Ansag and his student Michael in year 1953, we obtained the expression of the probability of a stochastic trajectory. And actually this zeta is the stochastic force, and by utilizing the equation of motion, that is the Langevin equation, one can immediately obtain the trajectory probability that is given in this paper. And if you consider a time reversal protocol, for example, this blue line is a forward protocol, and its time reversal is this red line, and you consider a time reversal trajectory of the forward trajectory, and then you do the ratio, of the two probabilities, that is a forward one and a time reversed one. And you will, after some algebra, you will find that the ratio is equal to the exponential of the forward trajectory heat functional. And actually this was the heat functional defined by Sekimoto. And this is a statement. And we call it the microscopic reversibility. It states that the ratio of the probability of a forward trajectory and its time reversed trajectory and the time reversal protocol is equal to the exponential of the heat functional. And the heat functional is heat function of the forward trajectory. And this is the most fundamental relation in the field of stochastic thermodynamics, because one can say that almost all the fluctuation theorems can be derived from this most detailed microscopic reversibility. For example, if you, after some co-screening, you obtain the so-called differential fluctuation theorem, and that is about the work, and also it's about the initial state and the final state. And if you do a further co-screening, you obtain the so-called Crookes fluctuation theorem. And if you do one step further co-screening, you obtain the famous Jasinski's equality. And that is why we call the microscopic reversibility the most detailed version of the fluctuation theorem. And it states, as I have shown, that it states about the probability ratios between a forward trajectory and a time reversed trajectory. And the natural question is about how about a quantum system? As we know that in an open quantum system, due to the uncertainty principle, there's no well-defined trajectories like in the classical system. However, people has come up with some ideas. For example, in this paper back to year 2009 by Peter and his collaborators, they come up with a very good idea that they consider an open quantum system, but assume it's a weak coupling, and the Hamiltonian of the system is denoted by H of S. And also this HB is the Hamiltonian of the mass, and the interaction is denoted as HSB. And then they introduce the so-called two-point measurement of the system, as well as over the heat bath. And the measurement of the system gives the change of the internal energy of the system. And the change of the energy in the heat bath gives the energy change of the heat bath. Actually, that is identified as heat. And by utilizing the first law of thermodynamics, one can obtain the work. We call it as a trajectory work, because the three quantities, change of internal energy, heat, and work, are not independent. Only two of them are independent. And then one can calculate the so-called joint probability distribution of the internal energy of the system and heat. And after some algebra, they are able to demonstrate that there is a relation, and that is about the joint probability distribution of internal energy and heat. And that is written in this way. Looks very similar to Crookes fluctuation theorem, but still it's different because they have two variables. One is the change of internal energy, another is heat. And due to the fact that only two of them are independent, so one can also rewrite this relation as this one. So this relation is a joint probability distribution of work and heat. And after the coarse graining, or simply you integrate out the degrees of freedom of the heat, one can immediately obtain the relation that is known as Crookes fluctuation theorem. So Peter and his collaborators has already formulated the fluctuation theorems in a weak coupling open quantum system in a very nice way. However, this is somewhat different from the classical version, because in classical system, we can construct all those fluctuation theorems, including Crookes fluctuation theorem and the Jasinski equality, from the so-called microscopic reversibility. So it might be interesting to ask the question, is that possible to analogously formulate the fluctuation theorem or formulate the microscopic reversibility in a weak coupling open quantum system? And actually there's some, for example, about in about the last 10 years or so, a group of physicists have come up with this idea. They have started the open quantum system, and especially its quantum optical system, and the system is described by the Lindblad-Most equation, and they have this kind of system has been extensively studied, but Jordan and Pecola and the collaborators and some other people have come up with this idea. They also identified the photon releasing and absorption during a trajectory as heat. And also they do two-point measurement at the beginning and at the end. And then they identify this as the internal energy change. And after subtracting the heat, and they define the trajectory work. And through this definition of trajectory work and the trajectory heat, they also formulate the fluctuation theorems in a very nice way. However, the problem is that this kind of system cannot be reduced to the classical Brownian motion. So as we know that in the stochastic system, thermodynamics, people usually use classical Brownian motion as the model to study work, heat, entropy production, and so on. So our motivation is to understand the trajectory work and heat in a quantum Brownian motion. And this model cannot be described by the Lindblad master equation. And also we hope that this system can, we can establish a connection between the open quantum system and the classical open system, like the Brownian motion. And then we realized that one may consider the possibility of introducing the concepts of work and heat along individual Feynman path, because Feynman's path integral formulation of quantum mechanics has the advantage of studying quantum to classical correspondence. And also we know that when we do the stationary phase approximation, the quantum trajectory will reduce to the classical trajectory. So that is the basic idea. Then let's come to the second part of my talk. How can we define, or how can we introduce such a concept of work and heat along every pair of Feynman paths? Let us first introduce the model that we study. That is the most extensively studied model in the field of quantum Brownian motion. It's called Caldeira-Leggett model. And this is a system, and this is the P is the momentum, and X is the coordinate. And the interaction Hamiltonian is just a linear interaction, and this is a counter term. And also the Bath Hamiltonian consists of a lot of harmonic oscillators, and the spectrum obeys like ohmic spectrum, so that in the high temperature limit, the dynamics of this system will be reduced to the classical Brownian motion. And actually, this model has been extensively studied in the past few decades, because people use it to study, for example, decoherence in an open quantum system, and has also accumulated a lot of techniques. And we hope that those methods or techniques will be helpful when we want to calculate the heat or work statistics in these open systems. And then let us come to the quantities that we want to calculate. And that is called the heat. And as I have mentioned that Peter and his collaborators has introduced the method of doing 2-point measurement over the heat bath. So initially, like if the system is in state M prime, B denotes the heat bath. And after some interaction with the environment, system interaction with the environment, and finally we make another measurement over the heat bath, and it is in state M. And then the difference of the outcomes of the two measurements over the heat bath gives the quantity of heat in one realization. And initially we assume that the heat bath is in some equilibrium, and this is the so-called transition probability. This USB is the unitary evolution operator over the composite system, the system plus the environment. And because we have assumed that it is a weak coupling, so the initial state is simply, it can be just a product state of the system and the heat bath. And we can construct the heat probability distribution function. And this is not a good quantity because it consists of a summation and also a delta function. So more convenient way is to consider the Fourier transform of this quantity. We call it a characteristic function of heat. And this can be written in this form. It's a trace of the products of several operators. And after solving this quantity, we can immediately obtain the moments of this heat distribution. For example, the first moment is equal to the average of heat, and the nth moment is equal to the nth derivative of this characteristic function of heat. And then we want to, how to calculate this characteristic function of heat. And a natural way is to consider the path integral approach, because in the past few decades, people has already extensively studied the reduced dynamics of the system in this Brownian motion. And the most convenient way in those study is the so-called path integral approach. By introducing the so-called Feynman-Vernon influence functional, the reduced density matrix of this system is can be written in this way. And this Sx, Sy are the actions of the forward and the backward evolution. And this Fv is the so-called influence functional, which encodes information of the environment. And when the interaction decays to zero, when there's no interaction with the heat bath, this factor is simply equals to 1. And then this is a unitary evolution, and this is an isolated quantum system. And when there's an interaction, this Fv encodes all information about the environment. And here X and Y are the forward path and the backward path. And here we can even write down the expression of the Feynman-Vernon influence functional. Here, L is the bath correlation function. It's related to the heat bath and its spectrum. And then we can similarly consider the characteristic function, because it looks very similar to the reduced density matrix of the system. And after writing the expression of the characteristic function of heat in the path integral form, we find that it's identical to the reduced density matrix, except that we have an extra phase factor, and that is e to the power of I nu q nu. And this expression of this q nu is equals to this one. And we call this as heat functional. The reason is that this is about the time evolution, and that is about the heat. So that is a Fourier transform. So we call, let us tentatively call this as a heat functional. And later I will show you that we have 3 independent ways to demonstrate that this is indeed the heat functional along a pair of Feynman paths. And we have several self-consistent checks. For example, first we can demonstrate the microscopic reversibility. That is a counterpart of the microscopic reversibility in classical open system. And this is the definition of heat, and this is the result. And I will show you how can we prove this relation. And for example, this is the so-called conditional path probability distribution. And this is the density matrix elements, and this is the forward path, and this is the backward path. And this is a probability distribution conditioned on the initial density matrix element. And they are equal to the exponential of Q. And Q is the heat functional along the forward path. And let me prove this relation. And it's actually quite straightforward because this is the probability distribution of the forward path. And this is a probability distribution of time reversed, because this is the evolution of the isolated system, and this is influence functional. And we can rewrite this expression, and we found that in comparison with its time reversal, there's a time symmetric part, and also there's a time asymmetric part. And when we do the ratio of the 2 probabilities, the time symmetric will cancel out, and the time asymmetric will be left. And this time asymmetric is identical to the heat functional as we have just defined. And this is the heat functional of the forward path.
Can I ask a question here?
Yes.
Yeah. So if I understand correctly, so far you haven't made any weak coupling approximation, right? So the influence function is exact, right?
We have made a weak coupling assumption.
You have, or you haven't?
Can you say again?
Did you make the weak coupling approximation here, or is it
Yes,
exact?
yes, we must, because for strong coupling, we don't know how to, for example, how to identify heat, because for a weak coupling, the two measurement over the bus can be identified as heat. But for strong coupling, that is not true.
Yeah, that's true. Yeah, but on the other side, the influence functional probably in this case can be obtained exactly, right? Because your path and the coupling is all linear, right?
Yes. So sorry, I didn't get your question. So you're
So
saying,
what I'm saying is that of course there is a problem with the definition of heat, but at least
yeah,
at the level of influence functional, this can be received exactly, right? Because you have the
yes,
linear coupling with the path.
you can solve it, but physically, I don't know what it is. I can't say it's a
Right.
characteristic of
And the
heat.
other question is this regarding this heat functional. It's interesting to see that the asymmetry is coming when the forward and the backward, or these two paths are talking, right? That's the asymmetric part. The symmetric part I could see is always either XX or YY. Would you like to make some comment about it, like why this is the case?
This is a good question. Frankly speaking, I can't make any further comments, because I feel that my opinion is that time asymmetry
Mhm,
is included in this influence functional.
Okay.
So
Thank
if this influence functional goes away, or if it is equal to 1 in an isolated system, the dynamics is time symmetric. There's
Thanks.
no time asymmetric.
Right.
So that
Okay.
is basically related to the
Great.
interaction with the bus.
Thank you.
Okay?
Yeah. Thanks.
Yeah, you're welcome. Mhm. Okay, so then we have proven the microscopic reversibility for this quantum Brownian motion in analogy to the classical system. And we hope that from this microscopic reversibility, we can prove other fluctuation theorems like Jasinski's equality. And that's what we are able to, I will show immediately. And we also want to make a few comments here. And when there's no heat bath, as I said, the influence functional equals to 1. So then the heat equals to 0, because that agrees with our intuition. And also the heat functional as a measure of time asymmetry, that actually the time asymmetry is included in the influence functional. And also this is a most fundamental relation in this open quantum system, because all the other fluctuation theorems regarding the non-equilibrium work can be derived from this relation. For example, let me show you how to derive Jasinski's equality from this relation. And we consider, for example, this is in a complex time plane, and we introduce the so-called internal energy functional. This is a Euclidean integral, and this is action. And we define this as the internal energy. Of course, in the classical limit, when h bar goes to 0, this reproduces the classical internal energy, because it equals to the kinetic energy plus the potential energy, and also some quantum correction term. And then by utilizing the first law of thermodynamics, as Peter has introduced in 2009, and we can introduce, or we can define the so-called work functional along a pair of Feynman paths. And then we can similarly write down this relation. It's the forward and the time. This is a forward and time reversal. And this is the initial thermal equilibrium distribution. And this is another thermal equilibrium distribution. This is a forward process, and this is a backward process. And if you multiply both left and right hand side with this numeric denominator, and then do the integral over all the paths, you do the path integral over all paths, you immediately obtain this relation. Because if you do the path integral over the right hand side, you obtain this one. And the left-hand side, the numerator, it's you do the path integral, it will be equals to 1 because the normalization condition of all of those Feynman paths. So we demonstrate again that based on the path, the heat function along individual Feynman paths, we prove the Jarzynski's equality. And also we can consider the quantum to classical correspondence, as I have mentioned very early in very beginning, that the formulation of fluctuation theorems based on those quantum trajectory and the quantum jump approach in quantum optical system does not have a well-defined classical system. But as we know that in this quantum Brownian motion, it has a well-defined classical limit. That is the classical Brownian motion. And actually, one can easily demonstrate that the heat function that I have just introduced can be reduced to the heat functional introduced by Sekimoto in 1998. And of course, I have to take the classical limit and assume the ohmic spectrum and the weak coupling strength. And then that means we demonstrate the quantum to classical transition at the level of individual trajectory. And similarly, we can consider the heat statistics. And if we take the so-called stationary phase approximation, only the classical trajectories will be kept, and the work functional also is equal to the heat functional is equal to the classical heat functional, and the integral is over the classical path, and then it is equal to the classical statistics of heat. So we demonstrate the quantum to classical correspondence of heat and heat statistics. And before the end of my talk, I also would like to emphasize that there are very relevant research to ours, and actually a group of people by Professor Aaron from France, and also Professor Yu from Konkuk University in Korea. They have come up with very similar ideas that they also define work and heat along Feynman paths, but it's interesting to see that their definition is actually quite different from ours. And so my feeling is that for a quantum system, there's no unique way. There's no unique way to define trajectory work or heat along Feynman paths. But in classical system, like in the classical Brownian motion, the definition of heat or work it is unique. So, and another thing that I want to mention is that the stochastic trajectory in a classical Brownian motion is measurable. So one can, you carry out an experiment to detect those trajectories. But in quantum system, in this quantum Brownian motion, even though we can mathematically, we can define the trajectory heat or work, but physically, I don't know how to measure this quantity. So it's more like a mathematical trick. It's not a physical reality. That is common that I want to mention. And
sorry, Haitao, can I quickly ask you a question on that slide?
Yes. Yes.
Yeah, I think I understand your point about the definitions not being equivalent on the trajectory level, but what about the averages?
Yeah, that is a good question. That's very tricky. So if you consider the average, actually there are some subtleties. Sometimes it's not equal to the average energy obtained from other methods like two-point measurement. So one should be extremely careful here.
Yeah,
it's not necessarily equal to the like average energy obtained from two-point measurement.
I see. Okay, thank you so much, Haitao.
Yeah, good question. Very good question. Okay. So I would also make a brief comment that actually in the we define the work functional along individual Feynman path. That is based on the Feynman's formulation of quantum mechanics. And the two-point measurement method is based on Schrödinger's version of quantum mechanics. Of course, they are equivalent, but I believe that the work functional along Feynman path brings more insights than the method was a concept based on two-point measurement, because as I have demonstrated that we can prove the quantum to classical correspondence of work and heat statistics and so on. But for if you define work trajectory work based on two-point measurement, you are not able to demonstrate the correspondence between quantum trajectory and classical trajectory. And some other advantages of this Feynman path integral formulation is you can calculate the, for example, quantum corrections to work functional, and also demonstrate the correspondence. And if you are interested in this topic, and there are some relevant references. And I think that is a summary of my talk. We define the trajectory heat along every pair of Feynman paths to formulate the first law of thermodynamics. And also the microscopic reversibility can be proven for the quantum Brownian motion. And also the fluctuation theorems, including Jaginski's equality, can be formulated based on the trajectory heat along Feynman path, and the correspondence between quantum trajectory heat and the classical trajectory heat are established in this model. So it brings more insights than the other method. And that's my talk. Thank you for your attention. Yeah, I think I stop here.
Thank you, Professor Chuan. Any questions?
Yeah, may I?
Please.
May I ask? Yeah. In the case of the 2-point measurement, I think you have also a proper classical limit, and it will agree with what you expect classically. Of course, also again restricted to recoupling. I mean, the problem one has with so to say fluctuating work and heat is not restricted to quantum mechanics. If you go to systems which couple strongly with each other, because you don't know how to separate, so to say, the total energy of your system.
Yes, I agree.
Interaction part, and about that you don't know where to actually put it, and some people have put it fully to the systems, some half and half, and so on. So there are all kinds of solutions. That's just a comment. Let me just ask. Have you also calculated the probability density of either work or heat based on this fluctuating path probabilities, and how do they compare to the 2-point measurement corresponding quantities?
Okay, so yeah, this is a good question. In one of our paper, let's see. In this paper, actually, we calculated work. That is a slightly different paper. We calculated work, and so Peter, your question is it equivalent or is it equal to the work statistics based on 2-point measurement?
As far as I understand, it is not equivalent, and therefore
it is equivalent.
And I mean, in a sense, it would be surprising if it were consistent, because in one case you really do the 2 measurements, and these 2 measurements will, in general, have an influence on the dynamics of the system, and therefore also on the work. That's specifically quantum mechanical, and that I mean, it's at least not obvious that you would do the same if you consider the trajectories.
Okay, this is a good question. As I said, actually here we we calculate, for example, we calculate the heat statistics, and it's equivalent to two-point measurement. The reason is that even though, for example, here, sorry, so here, look, this is equivalent to the, this is the heat statistics. We write it down in the class integral formulation, and then we introduce this heat functional. But that is a mathematical trick. It has nothing to do with experiment. We don't do any measurement over those paths because there's no way to do it. So this is equivalent to two-point measurement, this quantity, because we just write it down in this path integral form, and then we interpret it as the summation of all those Feynman's paths. That is just an interpretation. It has nothing to do with experiments. It has nothing to do with measurement. I hope
I think I see, and the reason why they the two expressions agree, so your and the 2-point measurement expression, is that here you assume the factorizing initial condition with
yes,
an initial bath state and also an initial system state, which
yes,
both commute with their respective Hamiltonians.
yes, yes.
Yeah, and therefore, so to say, that the first measurement has no
Effect
effect on the state,
on
and
the system.
therefore
Yes,
we get the same results with
yes, yes. That is why I emphasized that we consider only weak coupling. For strong coupling, as you said, even in classical system, it's not clear. So we don't know how to deal with strong coupling, but we assume that it's weak coupling, and then everything is clear. Yeah, that is. We don't know how to deal with strong coupling.
Okay, thank you.
Mm-hmm.
Can I have a quick question, please?
Oh, please.
Haitao, at the
Yeah.
sometime in one of your earlier slides, you mentioned that using the standard master equations like a Lindblad doesn't give you
Yes,
the
yes.
same results, right? I
Yeah.
can completely buy the statement, but what about a little bit more sophisticated master equations like a red field or something? I would expect in this weak coupling, at least a red field should give you the same results as what you obtain from your path integrals, but of course in weak coupling, nothing to do with strong coupling. But have you checked this? Or
No, I actually, okay, so let me show you the references. If you're interested in those, you may look at this review paper. People, this is a group of scientists. They are interested in this Lindblad master equation, and they come up with this very nice idea of trajectory heat and a trajectory work, and they formulated the fluctuation theorems and so on. So I think it's nice, but I don't know. I mean, I studied this path integral because in my opinion, this kind of master equation cannot be reduced to the classical Brownian motion, like a Fock-Planck equation. So that is why I didn't pay attention to this study. As you asked about the read field, I don't know if you can write it down in a path integral. I don't know how can we relate that master equation to like a Fock-Planck equation of a classical Brownian motion. That is, I don't know. I don't know how to collect the two, quantum and a classical.
But I
It's
think
really difficult.
Excuse me, I think in the case of red field, it should be possible
Yes.
to take the classical limit, and it
It's
will be
mhm.
the standard for
The standard Fokker-Planck. It's the Van Kampen expansion, basically.
Oh,
So
okay. I see.
these are the Van Kampen expansions, right? So
That
in the
might
red
be
field, you can do this.
that might be very interesting, but I sorry, I'm not familiar with that
Okay.
because
Thank you.
in my opinion, that they have very you know, in this formulation based on the Lindblad master equation, they have very different definition of trajectory heat. For
Sure.
example, they have some non-unitary evolution, and then there's some quantum jumps and a non-unitary evolution again. And only the energy change associated with those quantum jump. For example, this is a photon emission, and sometimes it's a photon absorption, and this is a detector. And the detector will be able to detect the photon emission or absorption, and they identify the photon absorption and the emission as heat. And also they measure the initial energy and the final energy, and the difference of the initial energy and the final energy gives the in the change of the internal energy. So by utilizing the first law of thermodynamics, the internal energy change minus the heat absorbed gives you the trajectory work. And that is quite intuitive, and experimentally it should be measurable. But my focus is not on this. My focus is on how can we construct a framework of stochastic thermodynamics in an open quantum system, and this framework can be have a classical correspondence. So we found that the Feynman's path integral might be the most convenient way, and it's quite different from this kind of quantum jump approach. Yeah,
Okay.
that's my answer.
Okay, are there any more quick questions? We're coming towards the end of the talk. Okay, if not, let's thank the professor and also all the other speakers in this session. And I